You ever get that feeling, that thrill, when something really complex just suddenly clicks?
Oh, absolutely. Like unlocking a new level.
Exactly. And that's what we're trying to do here on the deep dive. Make those dense topics, well, not just understandable, but really interesting.
Yeah, digging out those key aha moments, the discoveries that just change everything about how we see the world.
We're like, knowledge archaeologists.
Ah, I like that. Sifting through history for the game changers.
And today we're digging into the discovery of the electron and the nucleus, going back to, the late 1890s, early 1900s?
That's right. And we're using this great lecture as a source. What's really amazing is how, low-tech the experiments were.
Right, considering they completely overturned everything.
At the time, a lot of scientists genuinely felt physics was basically, done, just minor details left.
Wow, talk about being spectacularly wrong.
It's kind of humbling, isn't it? While they were saying that, the whole picture was about to be redrawn.
And think about the challenge. They were trying to study things you literally cannot see. How do you even start?
That's the genius of it, isn't it? Clever experiments, careful observation, they figured out how to see the invisible, in a way.
Okay, let's get into it. First up, the electron. J.J. Thomson, late 1890s, cathode rays. What did his setup actually look like?
Okay, so picture this. A glass tube, most of the air pumped out, a vacuum tube, basically. Inside, you've got two bits of metal, electrodes, one negative the cathode and one positive the anode.
Right.
Apply a high voltage, and boom, you get this invisible stream, the cathode rays, shooting from the negative to the positive end.
Invisible, so how did he see them?
Good question. He had a screen at the end coated with something phosphorescent. It glowed where the rays hit it.
Okay, like an old TV screen, sort of?
Exactly like that. And initially, with nothing else going on, the ray just made a dot straight ahead.
Makes sense.
Yeah.
But then he added the electric plates.
Yes. He put two plates near the path of the ray, one charged positive, one negative.
And what happened? Did the dot move?
It did. The ray bent, and crucially, it bent towards the positive plate.
So that told him something right away.
Instantly. If it's attracted to positive, the ray itself must be made of particles carrying a negative charge.
Simple logic, but profound.
And Thomson knew his physics. He knew the amount of bending, the deflection, depended on two things.
Which were?
The particle's charge, more bend, and its mass. Less mass, more bend. It's inversely proportional to mass.
Got it. More charge or less mass makes it easier to push around with the electric field.
Precisely. But he didn't stop there. He cranked up the voltage on those plates, even higher.
Okay. Expecting maybe a bigger bend?
Probably. But he saw something else, too. A second spot appeared on the screen, much fainter, much less deflected.
A second spot, going the other way.
Exactly. This one bent slightly towards the negative plate.
Whoa. Okay, so that means...
That means there wasn't just a negative particle in the ray. There had to be a positive one, too.
Mind blown.
Right.
Two particles.
Two particles. And the tiny deflection of the positive one, even with more voltage, that was also a huge clue.
About its mass and charge again?
Right. Same principle. Tiny deflection implies either very little positive charge or a whole lot more mass.
So how did he figure out which it was? He knew atoms are normally neutral?
Yeah, that was key. For the atom to be neutral overall, the total positive charge must equal the total negative charge. The amounts have to balance out.
Okay, so the charges are equal in magnitude, +1, -1 kind of thing.
Effectively, yes. So the charges are the same magnitude, but the deflections are wildly different.
It has to be the mass.
It has to be the mass. The negative particle, bending so easily, must be incredibly light compared to the positive one.
How much lighter?
But 2,000 times lighter, just unbelievably small.
Wow, 2,000 times. And this tiny negative speck, that's the electron.
That's our electron, later named, of course. And another experiment pinned down its actual mass, something like 9 × 10⁻31 kilograms. Vanishingly small.
So, just to really nail this down, Thomson's experiment, cathode ray tube, bending rays, proved atoms aren't fundamental.
Shatter that idea.
Yeah.
Completely. Show there are things inside atoms. Subatomic particles.
What a shock that must have been, that scientific confidence you mentioned.
Yeah, it really took a hit. It showed that, you can't assume you know everything. New data can change the game entirely.
Okay, so we have electrons, but what about that heavier positive part? That brings us to Rutherford, right? And the nucleus.
Ernest Rutherford, yeah. A bit later, early 1900s. And he was deep into studying radioactivity. Apparently even got samples from Marie Curie herself.
Amazing. The lecture mentioned they were pretty casual about handling radioactive stuff back then.
Oh, yeah. Different times, definitely a different understanding of the risks. But his work led to this landmark experiment. He was using alpha particles.
Alpha particles. Those are positive, right? Ejected by radioactive atoms.
Exactly. Positively charged, relatively heavy. So his setup, a source shooting out these alpha particles, a detector to count them, and in between, a super thin sheet of gold foil.
Thin gold foil. Okay. What did he expect to see shooting particles at foil?
Well, first, without the foil, his detector was clicking like crazy, about 132,000 alpha particles per minute, a steady stream.
Got it. Then he puts the gold foil in the way?
Yeah, almost nothing changed. The vast majority of particles just zip straight through, maybe a tiny drop in the count, but essentially straight through.
Straight through. That seems weird. Shouldn't they hit the gold atoms and bounce up?
That's what the old plum pudding model, sort of Thomson's idea, might suggest. But this result pointed somewhere else.
Meaning?
Meaning the gold atoms must be mostly empty space. If almost everything goes through, there can't be much in the way.
Okay, mostly empty, but not completely empty, right? There's that student experiment.
Ah, yes, the crucial follow-up. Rutherford had an undergrad, Geiger, and Marsden actually did it, move the detector, not just behind the foil, but off to the side even, in front of it.
To see if anything bounced back, even though they probably thought nothing would.
Exactly. Low expectations. But they found something.
Don't tell me.
A tiny, tiny number of alpha particles, maybe 20 per minute compared to the 132,000 going through, actually bounced almost straight back scattered.
20 out of 132,000. That's what, like 0.02%? It's almost nothing.
Almost nothing, but everything in terms of understanding. Rutherford was floored, he famously said.
Oh, the tissue paper quote.
Yes. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you.
It just shouldn't happen based on the mostly empty space idea alone.
It shouldn't.
Yeah.
So how do you explain it? There must be something inside the atom that's incredibly small, incredibly dense, and positively charged enough to repel the positive alpha particle and make it recoil like that.
Like hitting a tiny, super heavy cannonball hidden in a huge, empty warehouse.
Perfect analogy. That tiny, dense core. That's the nucleus.
So Rutherford's model emerges. Tiny, positive nucleus at the center, electrons somewhere out in the vast emptiness.
Yep. Mostly empty space, a dense positive center, and the negative electrons orbiting somehow, balancing the charge. A totally different picture.
And this balance of charge, it leads to the Z notation, right?
It does. Z is the atomic number. It tells you how many units of positive charge, how many protons are in the nucleus. So the nucleus has a charge of plus Z, where he is that fundamental unit of charge.
And to be neutral.
You need Z electrons, each with charge E, somewhere in that empty space. Total charge, 0.
Amazing. And Rutherford even estimated the size of this nucleus from the scattering data.
He did. Based on how many particles bounce back, he calculated the nucleus diameter to be around 10 to the minus 14 meters. Compare that to the whole atom, which is 10 to the minus 10 meters.
It's minuscule, like a fly in a cathedral.
Exactly. Unimaginably small and dense.
The lecture had that great classroom demo analogy, too. Styrofoam and ping pong balls.
Right. Imagine a frame, that's your gold foil area. Scatter a few styrofoam balls inside. Those are your nuclei.
Okay.
Then you throw ping pong balls, the alpha particles, at the frame. Most will miss the styrofoam and go right through the empty space.
Just like the alpha particles through the foil?
But occasionally, a ping pong ball hits a styrofoam ball dead on.
And bounces back? Just like the backscattering.
Precisely. And you can actually use that setup, counting how many bounce back, knowing how many styrofoam balls there are in the area.
To calculate the size of the styrofoam nucleus?
You got it. The lecturer mentioned they did this and got pretty close to the actual size of the styrofoam balls, like 2.7 centimeters versus 2.5 centimeters. It shows the principle works.
That's a fantastic way to visualize it. Okay, so Rutherford gives us this new model. Tiny positive nucleus electrons out in the void. But that immediately creates a new problem, doesn't it?
Yeah, a huge one. The biggest one yet, maybe. If the nucleus is positive and electrons are negative,
opposites attract. Why don't the electrons just spiral straight into the nucleus? Zap.
Exactly. We know about electrostatic attraction. Coulomb's law, which the lecture brings up, describes it perfectly.
Can you quickly recap Coulomb's law for us, just the gist?
Sure. It basically says the force between two charges gets stronger the more charge they have, and much stronger the closer they get. It's an inverse square law, half the distance, 4 times the force.
So think about hydrogen. 1 proton nucleus, 1 electron. If they're far apart, the pull is weak.
Right. But as that electron gets closer,
the pull gets stronger and stronger, infinitely strong at zero distance.
According to classical physics, yes. The lecture had that clicker question, right? What's the force at zero distance? Infinitely attractive.
But atoms don't collapse. They're stable. We exist. So Coulomb's law seems to predict disaster.
Complete disaster. There's this massive contradiction between the classical prediction and, well, reality.
And it's not just Coulomb's law, it's basic mechanics too, right?
Oh. Yet Newton's second law. That attractive force should cause the electron to accelerate, to move.
And the calculation in the lecture showed what? How fast should it collapse?
Incredibly fast. Based on classical physics, the electron should spiral into the proton in about 0.1 nanoseconds.
A tenth of a billionth of a second.
Practically instantaneous. Poof.
So classical physics, Coulomb's law, and Newton's laws, they just break down at this scale. They can't explain why atoms are stable?
They completely fail, utterly. Which meant that our fundamental understanding of physics, the rules we thought governed everything, needed a radical overhaul for the atomic world.
Which paved the way for?
Quantum mechanics.
Yeah.
A whole new set of rules to describe how matter behaves when it's really, really small.
Wow. So solving the mystery of the atom's parts just opened up an even deeper mystery about why it holds together.
That's often how science works. Answers lead to bigger questions. And it's interesting, that idea of stability. The lecture hinted at a connection to buffers.
Yeah, that was a neat little aside, like how buffers resist pH change, maintain stability in chemistry or biology. It's sort of a macro-level echo of the atom needing stability against collapse. Different scales, similar concept of maintaining equilibrium.
It is a nice parallel. Shows how fundamental these ideas of stability and structure are across science.
Well, this has been fascinating, going from thinking atoms were solid little balls to finding electrons in this tiny nucleus, all with, fairly basic lab gear.
Ingenious experiments, though, really speaks to the power of just clever thinking and careful observation. Groundbreaking stuff.
And it totally reshaped our view of matter. A huge reminder that what seems settled science can just be overturned by new evidence.
Absolutely.
Right.
Science is always provisional, always ready to be updated. The story's never truly finished.
And discovering the electron and nucleus didn't end the story, it just led to the next chapter. Why don't atoms collapse? Which led to quantum mechanics. It just keeps going.
One mystery unlocks the next. That's the adventure.
It really is. So as you're listening, just think about that these invisible particles discovered over a century ago form the basis of everything around us. Their discovery changed everything.
And continues to shape our understanding today.
So here's a final thought for you to chew on. What current seemingly rock-solid scientific ideas might just be waiting for their own Rutherford moment, their own unexpected discovery that changes the game completely.